All right, so here's just a few more slides to wrap up our presentation on Chapter 4, Biomechanics. Last spoke on Monday, where we left off was factors affecting strength. And most of the literature speaks to two components that are mostly going to affect strength. Those are the neurological components, which I already spoke to, and the cross-sectional area or the size. All things being equal, a larger muscle is stronger and can produce more force than a smaller muscle. But there are some other areas on how we display strength, right? And that's the next slide, where pennation angle, muscle length, and joint angle. Pennation angle is largely determined just by our genetics. Some people say pennation angle is trainable. I have never worked with a client focusing on developing a larger pennation angle. That's just more of a practical piece. But what is pennation angle? And that's the angle with which your muscle fibers align with the tendon. So our tendon kind of runs the length of the muscle almost, or excuse me, the length of the bone, right? Or it runs in line or parallel with the bone. A muscle fiber that is angled away from the tendon, right, is considered to be pennate or have some sort of pennation angle. Usually when we say something that's pennate, we are speaking that it's in excess of 15 degrees of the tendon. So why is this important? We found that a larger pennation angle may be able to produce more force, but this is not without some issues where a larger pennation angle may also have a lower contraction velocity. Right. I got a picture. Some of you guys are probably confused on what that actually means. One, review in your text, but I've got a picture on the next slide which might help you guys visualize a pennation angle a little bit better. The next two I think are a little bit related, and that's muscle length and joint angle. All right. So there exists a theoretical optimal length to produce force for each muscle, and this varies for each muscle, but the simplest way to describe this is if you remember our conversation about muscular shortening and sliding filament theory, where we have our actin and our myosin overlap, and then as we go through that power stroke, they pull together and they shorten, right? So in theory, right, what we should say, right, because there's various cross bridges, if a muscle looks like this, right, there's only like one cross bridge head that can actually pull to produce force, right? So this would not be optimal, right? Because there's only one cross bridge head. Conversely, if the muscle looks like this, it cannot further shorten. It's in a shortened position already, and it can't further shorten to produce force, right? This is as far as it goes. So there exists some theoretical optimal length, something like this, to produce force, where there's various crossbridge heads, one here, one here, one here, one here, that can go through that sliding filament theory component and shorten to produce force, right? Now, this optimal length is heavily related to our joint angles. So I'm going to go ahead, hopefully you guys can see me. If we think about a vertical jump, I mean, you guys won't be able to see me from this angle, but if we think about a vertical jump, right? And we'll talk about this a little when we get to the chapter on plyometrics. When we go through a vertical jump, an athlete, or if we're doing a vertical jump test, they never stand tall. So I'm not standing straight up, right? Where my muscles are in the most lengthened position, right? I am conversely, I'm not standing all the way down at the bottom from trying to jump as high as possible. Usually, it's down and up to about here and then up. So we'll say for the muscles of the quadricep, right, there's this optimal length, which is not all the way lengthened and not all the way shortened to produce as much force as possible to have me jump as high as possible, right? And that muscle length is related to my joint angle, specifically the knees and the hips, right? So if I bend just a little bit at the knees, right, okay, there's some shortening going on there, or excuse me, some lengthening going on there, right? But if I bend a little bit more, right? Is that the optimal angle? Maybe. If I bend all the way down, we know that's usually not the optimal angle. No one actually does a vertical jump test all the way from a deep squat, right? So that's why muscle length and joint angle are related, right? So here's a picture of Kai Green, famous bodybuilder. Oh my, let's see. Unfortunately, I don't think you can see the picture because my face is over the leg specifically that I wanted you guys to see. His left leg, if you look at the muscles of his quadricep on his left leg, you'll see some feather-like muscle fibers that are extremely pennate, pennate to the highest degree. So what I'll have to do is maybe I'll have to upload that picture and you guys can get a better idea of what a pennate angle looks like. So factors affecting strength. Other factors that affect strength are the external objects that we are moving, right? So this is the force velocity curve. It was first created by A.V. Hill in like I want to say 1938, I believe. And this is basically what it states is, as force production increases, our velocity typically decreases. And conversely, as our velocity increases, our force usually decreases. So the best example of this is doing a 1 rep max on a lift. So let's say a 1 rep max on a squat or a 1 rep max on a bench press. Typically, as we lift those weights, the barbell velocity decreases, which you'll see some people as they're grinding as they're doing a lift. The velocity for us to actually express that force decreases, right? But there's other things that we move which might have a higher velocity. So if we go a little bit, if you could follow my cursor, I'm right here at the max or absolute strength end. As we go a little bit up here where our velocity is a little bit faster, right, in this accelerative strength zone, maybe we're talking something like a push press, right, where a push press, if you guys don't know, is a little bit faster, but it's still relatively heavy weight. People push press 200 pounds, 300 pounds pretty easily. As we move up this strength curve, right, our velocity is increasing a little bit more. Maybe we're talking about, maybe some more sporting movements. Something like this right here would be maybe throwing a shot put, right? A shot put's about 16 pounds, 12 pounds, depending at what level you're talking about. A shot put is still relatively heavy, but the speed at which we move a shot put is much greater than the speed at which we move a 1 repetition on the bench press. If we go all the way up here on this force velocity curve, right? An example of this might be throwing a baseball, where the weight of a baseball is much lighter than the weight of a shot put, so the force required to move the baseball is much less. However, the velocity is significantly higher. All right, so that's the force velocity curve. In terms of practicality, I do think about the force velocity curve fairly often when thinking about the athletes I'm working with, and specific training blocks. I might develop a program where we're focusing a little bit more on max or absolute strength. We spend most of our time here, but there's definitely some training blocks where I'm focusing on like starting strength or speed strength, somewhere in these spectrums. All right. So some other things that could affect strength are strength to mass ratio, and this is really more an expression of power, right? So there might be an athlete who can deadlift something like 300 pounds, but only weigh $130 or $140, versus an athlete that can deadlift 400 pounds, but that athlete might weigh 250, right? What happens is, in terms of speed or velocity or power, more likely than not, that athlete who's much lighter, deadlifting 300 pounds, his strength to mass ratio is higher than that heavier athlete. All right. I also have a bullet point here where improvements in size can help or hurt an athlete. And this goes really for most sports. Oftentimes I think when working with parents, when speaking to parents, they say they don't want their young athlete to get too bulky. That's a big fear of theirs. While you have to understand and recognize that could happen, The likelihood of that happening when working with like, high school or even college athletes is very small. Um, you know, Eric Cressy, who I've already spoken to about being an influential person in my life, he has this saying for pitchers, right? Where the saying is mass equals gas. Mass equals gas. And what he means by that is to throw fast as a pitcher, usually the best way for like a high school athlete is put a few pounds on. For a high school pitcher to go from 160 to 175 can be incredibly helpful. I am a high school sprints coach, and oftentimes I'm telling my sprinters they need to put on 5, 10, 15 pounds over the course of 1, 2, 3 years to be faster. There is obvious situations where that could be negative. Obviously, if their force production, if their velocity decreases as they add weight, that's going to be a negative. But that's something as a coach you kind of have to evaluate. So up to this point, I've talked a little bit about concentric. I asked you guys, what essentially is this? Concentric is muscle shortening. The opposite of muscle shortening is muscle lengthening, and that's eccentric. And then isometric is basically a static hold where the length of the muscle does not change. So just in terms of like actual movements, if the easiest example would be a bicep curl. So as I curl up, right, this would be the concentric portion, and the muscle would be shortening. The bicep muscle would be shortening. As I lower, my muscle is lengthening, and this would be the eccentric component, right? If I were to hold a dumbbell right here for, let's say, 20 seconds, that would be some sort of isometric where the length is not shortening or lengthening, right? So those are the concentric, isometric, and eccentric components. From a practical training standpoint, we use concentric, isometric, and eccentric focuses all the time. Manipulating tempo on concentric and eccentric, incredibly important. Doing isometrics, incredibly important. For me, when working with athletes, there's a few other more advanced components to this. What we know, this is important. What we know is that muscle damage takes place primarily in the eccentric phase of resistance training. That's very important, so I'm going to say it again. Most muscle damage, good damage, I'm not just saying like getting hurt. Most muscle damage, most things that's going to create DOMS, delayed onset muscle soreness, is going to take place during the eccentric component of resistance training. So if you do 100 bicep curls, right, next day your biceps are super sore, right? A lot of research has showed that they are sore because as you curl this component, having a controlled eccentric curl, the eccentric component, this component right here, is what's causing a lot of that DOMS, and a decent amount of research, not just being sore, but also benefit or adaptation is muscular hypertrophy. So for me, right, when I'm working with clients, we could take that information and we'll use it on two ends of the spectrum. If I have a client that has a championship meet or something very important, maybe we remove the eccentric component from a lift and do primarily concentrics, so they're not super sore, there's not a lot of muscle damage going into their next championship meet. So what does that mean? How do you remove the eccentric? So typically like sled sprints or sled pushes. So a sled where you're pushing one way and then stepping into it doesn't really have an eccentric component. That's one example. There's plenty of others. All sorts of like plyometric stuff where we focus on the concentric. That really focuses on the concentric with very little eccentric loading. All right, so that's one example of that. Conversely, if we're trying to focus on muscular hypertrophy, we might really focus on the eccentric component. So a gym term for this might be doing something called a negative, right? So what we might do on a dumbbell curl, if we're trying to focus on growing our biceps really well, we might curl, and then slowly lower. 1, 2, 3, 4, 5, 6. Curl. 1, 2. So focusing a little extra on that eccentric component may lead to better hypertrophy of a muscle. All right. So those are some examples of how we can relate that to in the context of training. And I just threw in this extra slide at the end. Sometimes we have slightly more advanced discussions that are usually beyond the scope of the textbook. Oftentimes in texts, you'll see that force velocity curve that I showed you on slide, I think it was 16 or 17, right? And I showed you how as force increases, our velocity decreases. There is another component to that, right? That force velocity curve that you oftentimes see is just for the concentric component of a movement or lift. The other end of that spectrum is the eccentric component, right? And this graph, right, really has several implications, but I'm going to give you guys just one focus because, you know, it's already 16 minutes and I don't want to overload you guys. We're week 1, right? What this graph really shows you, right, if you look at the y-axis being force, the eccentric component, you can actually have a larger force on the eccentric component than you have the concentric component, right? So to apply this to training, what we know is that during the eccentric component, your muscle, right, can handle larger loads on the eccentric component than it can the concentric component. So what does that mean? My muscles, let's say of my quadriceps when I'm squatting, can handle a larger load lowering than it can on the concentric component, the raising component in a squat, right? So what you'll see is sometimes people will take advantage of this principle by overloading the eccentric component of the lift because their muscles can handle a larger load in the eccentric component. All right. Now, this is a little bit more advanced, and we don't really teach this that much. But again, within the context of training, you can start to focus on this. You know, whether I have a power lifter or some sort of like sprinter, thrower, whatever it is, there are very specific situations where we might use an overload eccentric, where we overload that eccentric component to help develop or maximize the eccentric phase of any type of lifts. All right. If you guys have any questions about this, feel free to bring this up at our next class because we're going to start, the first 5-10 minutes of our next class just reviewing and talking about some of this stuff.